Phil.
Wow.
All right, let's start. We'll continue on the fundamentals in interferometry. Just follow on Jonathan's introduction of radio astronomy and also Kato's talk on sort of two-element interferometry and some of the basics. Hopefully with coffee and you can actually, you're re-energized. And as I mentioned before, so there are two reference books that I found very useful. One is this Since the Imaging Radio Astronomy that came out of a series of the NREO VOA Summer School. And so this is really a good material to use, and also Interferometry Since the Radio Astronomy by Thompson, Moran, and Svensson that you can actually download from Springer's website. My talk also used some of the materials in Rick Hurley's lecture in VOA Summer School here. Okay, so the goal of this is the all right. So the goal of this lecture is really to derive a general relation between the specific intensities of an astronomical source. So sometimes we interchange the terms brightness distribution in the sky and the visibilities that we measure with interferometer. And this is also known as Van Cittert-Zernike Theorem. And there are some maths that we'll go through here. And also, in the second part of my lecture, we'll introduce and reinforce some of the concept of spatial frequencies and how that relate to baselines. All right, so we know that the electric field is a vector, and those are in boldface. But supposedly, we can decompose them into a scalar in the monochromatic components of this. And here's the geometry we're referring to. So on the surface of the Earth, supposedly you have two antennas that's separated by a baseline, that capital D. And so you have an astronomical source in the celestial sphere that at the direction of R naught, and the subtend of a solid angle at the also direction of S0. So so then you have this scalar component of the electric field actually is really the electric field at the source that modified by this propagation factor. And here you have the 2 pi nu and R naught subtract by small r, and that is just the delay that divided by speed of light. So that's the amount of phase delay that you're actually experiencing for the signal. And also on top of that, the amplitude of this field also got reduced by the factor 1 over R naught subtracted by R. So that's just a simple geometry here. All right. So supposedly, now let's just define this cross correlation function of V as a frequency of nu, and this is also sometimes also referred to as spatial coherence function here, or visibilities. And if you plug in the terms that we're here, what you have is just the integral of over those two elements on the surface of the sphere, ds1, ds2, and each of them are respectively from antenna 1 and antenna 2. So they're all delayed by corresponding amount in the distance, and also modified by this factor of 1 over r minus small r. All right. Okay, so let's make an assumption here that assume that radiation from different positions in a source actually are not coherent. So that actually can simplify this integral greatly, because those are the cross correlation of the two actually is 0 unless the radiation is coming from the same position here. All right. That assumption here means that there's no long-term phase relation between the emission from different points in the celestial region. And that is a pretty good assumption, although actually this will break down in some cases, like scattering, illumination, the screening of common source. But in a lot of our applications, this is generally a valid assumption. So feel free to interrupt me if you have questions. All right. Okay, so then we have this integral actually just break down into a very simple form here. All right. And I want to introduce one is S, the small s in boldface, and that's the direction, unit direction vector, okay, in the direction of R. And also specific intensity that was discussed in the first two lectures, and that is just this E squared times R naught squared, all right? And also, you can replace in this ds with R naught squared times d omega. Omega is the solid angle that's subtended by astronomical objects with respect to your telescope. All right. So, and also remember the fact that R naught, big R naught, is much greater than small r, because as your astronomical sources, we're assuming is infinite distance with respect to the baselines or the antenna locations on the Earth. All right, so then this relation can further be simplified. All right, so this visibility of R1, R2 becomes the integral of specific intensities in direction of S and times this e to the 2. By the way, I use I instead of j here for imaginary number, 2i pi nu, that's the cross product of S times R1 minus R2 divided by C. Okay, so this is one of the fundamental relation in the aperture synthesis in radio astronomy, and as you can see that where this will get to. So one of the interesting aspects of this equation is that actually this integral is not dependent with respect to the actual locations R1 and R2, but it's the difference vector. So this is the baseline vector as we defined earlier. All right, so if we introduce a rectangular coordinate system here, we have X, Y, and Z with and also U and V. Okay, so the unit direction vector here is related to cosine of those angles, L and M and N here. And that is the unit directional vector here, all right, S. And D can be decomposed in the three-dimension coordinate here is d of x, d of y, and d of z. So those are three components of your baselines. And here I define u, b, and w. So those are the u is dx divided by lambda. It's the wavelengths you observe, and the v is the dy divided by lambda, and w is dz divided by lambda. All right. Just to place this, how this coordinates related to the direction of sky. So this is an astronomical source. So then you have this visibility or spatial coherence function is written as this integral of specific intensity times 2 I pi nu s over this. This is just a repeat of the same relation here, and can be written as this, right? So you have S dot E here would become U times L plus V times M plus W times N. All right? Okay, so this kind of look like a Fourier transform that we want to get to, but you have actually a W and N dependence here. So it's not a three-dimensional Fourier transform. All right, but we're almost there. So let's make another important assumption here. So assume that the object we observe is small in angular size. All right. So then you can actually expand this in the Taylor series because L and M are small relative to 1 here, right? So that just becomes 1 minus theta squared divided by half. It's just simple Taylor expansion. So then you can rewrite this visibility function as a function of u, v, and w. And one nice thing is that you can actually pull out this w dependence outside of the integral. And then you have another term is w theta squared divided by 2. That's depend on L and M here. All right. So if your object is small here, and then you can actually assume, and this is much less than 1, w times theta squared. So you can ignore this term and also ignore those terms here. And then you can rewrite this relation into this visibility function actually is a two-dimensional Fourier transform of u and v here related to the specific intensity of your astronomical object. And sometimes we redefine the modified visibilities because to get rid of this term here. And that is actually what we often refer to when Cittert-Zernike Theorem, and that was first derived in optics in 1930s. And that is a basis of a lot of we do, and you'll probably be seeing this relation in later lectures when we talk about imaging and Fourier transform imaging reconstruction here. So what does it say is that if you actually have visibilities measured with a interferometer, you can get this back. You can get your brightness distribution back by inverse Fourier transformation here. So this is just pulling this out. All right. Okay. So one of the things you can think of this is that the interferometer is decomposing your astronomical source into different Fourier components, and those Fourier components are defined by u and v in your baselines, and that's what you measure in the cross correlation, those visibilities. The idea is that to take that Fourier transform back to get the specific intensity distribution of the object. All right. So I'm going this somewhat quickly. I think I don't know, Kato, whether our slides will be distributed with because the detailed mathematics again actually just go through once we have those material, give it to you. All right. Okay. So the in both Jonathan's and Kato's talk, we discuss about why interferometry. The interferometry is the idea of working with in radio wavelengths. You really need a really large aperture to deliver acceptable angular resolution for astronomical studies. So that's why you have the antennas. But those are not perfect system. Now, one is Kato mentioned that you actually lose sensitivity. Right. The second is actually you can think of it's really, really bad optics because you're not, say if you have a kilometer interferometer, so you can think of there's a lot of empty spaces not filled. So that'll give you images very, very, very difficult. So one of the ideas that was important in radio astronomy is radiosynthesis, and that's sort of the next thing I want to discuss. So one thing is that when you have the interferometer that we're not sampling this UMV continuously because your antennas are discrete. So you have discrete baselines here, right? So let's just assume introduce the sampling function of UMV, SUMV. So when you have a data point measure at U0 and V0, and you have the sampling function is 1, and elsewhere is 0. All right. So what we have is not actually a true distribution of astronomical source, but rather a dirty image we call. So it's I d of nu of Ln. All right. So that is what we measure, what we actually get. So the question is, how do you actually increase this sampling, right? So that is the idea of radiosynthesis here. So let's work out the Fourier transform. Qizhou, I've already discussed. You have the product of the two here. So actually, your dirty image is the convolution of your true distribution, brightness distribution with this dirty beam here. All right, so the dirty beam is equivalent of a point spread function in optics, and that is reflective of your sampling function of your in your visibilities. All right, there's another consideration that for radio antennas, they also they have this reception patterns of so that's also depend on L and M. So what you actually measure of your brightness distribution also modified by this antenna reception pattern here. All right, that is something that sometimes we say whether your image is primarily being corrected. That's normally is also involved. And I'm not going to go through spectroscopy, although I think maybe in our later when we actually taking the data, we will be looking at some of the spectral lines, except that to point out there's another Fourier transform relation. So when you have the visibility U, V, and nu, so this PowerPoint it's very conveniently look at very similar. All right, UV and frequency. All right, with this delay of tau, and Qizhou actually discussed this a little bit in his lecture. All right, so how do we improve this sampling function here? And that's so supposedly we have a two element here, antenna 1 and antenna 2, that they separated by a baseline of D. And you have a point source or paramplanetary waves coming in at the point source at the infinite distance from those antennas. So you have paramplanetary waves coming in. So what you have is this so-called fringe pattern here, right? So this is the directions, and this overall pattern is the antenna reception pattern. All right. So supposedly, if this is your telescope, this will be image will be very bad, right? So you have a point source supposed to be power only, all the power is in here, but gets spread out. So it's quite dirty, right? So you can think of this is a Fourier transform of a point source, in fact, right? Now, if you have three antennas, that gives you the three unique baselines. And Qizhou mentioned that actually your fringe pattern, the frequency will depends on the separation. So for those shorter separations in the antenna baselines, you have this kind of wider fringe patterns. So what you have is that if you add them three up, you add up, of course, at the center, but also in some other positions, they cancel out. You suddenly, even with three baselines, you are improving your quality of the image by improving your point spread function or instantaneous the point source response here. All right. Supposedly, if you have 6 antennas here, or 4 antennas, you have 6 baselines. And as you can see, that immediately you get dramatic improvement in here. So one of the things about radio interferometer is that you need to increase number of antennas. But if you just take instantaneous observations, you still have very limited sampling in UV space. So that's what this rotation, Earth rotation synthesis comes in. And Johnson mentioned this is the 1974 Nobel Prize for invention of radio synthesis technique by Martin Ryle, and also together with, as you all know, discovery pulsars. So what I took here is a lecture that Martin Ryle gave and that was reproduced in 1975 Science. So the idea is that, say, this is the surface, that's the Earth that you're looking at from the North Pole here. So you have an antenna here, antenna here. So with the Earth rotation here, in 24 hours, actually, you are produced sampling like a circle here. All right. Now, if you have the Earth, you have the pair of antennas somewhere in the different in northern latitude through the Earth rotation, and this is the U and V data points. So you have point 1 correspond to here, and point 2 correspond to here, point 3 correspond to here. So when you have the transit, here, that's point 2, you have maximum east-west baselines, and the smallest north-south baseline in B. All right, and when during the rise and the set, you have minimum east-west baselines, but then you have maximum north-south baseline. All right, so this is really the idea that if you have a bunch of antennas attract the source as it rise, transit, and set, you can really populate the data points in U of V, because even though your antenna baseline is fixed, your projected baseline in the direction of sky change as you track the source. All right, so if you take the Fourier transform in the 2D, and you really can improve this point spread function. So this is sort of a dirty beam that you typically see in here, that you have the power mostly in the main lobe, and then you have some of the side lobes. All right. Here's another just example done with EHT. As you can see that you have different baselines, what's shown here on the surface of the Earth. And this is the visibility coverage, U and V in giga lambda. And this is the image, corresponding image of M87 supermassive black hole. As you can see that, let's start again. So you have first, you have one baseline here, and you have a lousy image. As you're adding more antennas, as Earth rotates, you'll populate those data points in this visibility domain that really actually yield much nicer image of this supermassive black hole. All right, so I just want to introduce another concept. In the Fourier transform, as you can see that as Carlo mentioned, that when you have the large spatially extended source, the Fourier transform of it is actually narrower. In fact, the 4-width half max of those two curves, if you multiply those two, that's approximately 1. So there you have the inverse relation. So if you have a point-like source in the visibility, actually the visibility function as power as a function of baselines is a lot more extended. All right, so another way to look at it is that when you have short baselines, your information is coming from spatially extended structure. All right, so that's important, quite important concept when we talk about sort of short spacings in observations. I think I just want to leave you one of the examples that we've done in the Astronomy 191 back in Cambridge. This is Payton's class report, observations of a protoplanetary system HD 34700. So this is just a demonstration. This is the UV coverage that obtained with the SMA, and those are U and V in meters. And that's a Fourier transform. So that's your dirty beam. As you can see that you see those silos, where most of the power actually is at the center. And this is the dirty image. You can think of if this would be your true image, and that's the convolution of the dirty image, dirty beam, and true image. That's your dirty image. As you can see that your eyes, right? So there's an object here. There's another object here. This is, by the way, 1.3 millimeter continuum, mostly coming from dust in the circumstellar disk around this circumbinary system here, a binary system. All right, so you see that's the main power here, and that's the there's a secondary source here. So we'll be discussing about deconvolution later on in this, and I just want to sort of flesh this out. And want to leave you some of the currently commonly used interferometers. This is a very large array in New Mexico, and this is the Atacama Large Millimeter Summoning Array in northern Chile, Atacama Desert. And hopefully you get to visit and see the SMA later this week. And this is NOEMA. This is supposed to be a 12 element of 50-meter telescopes in the Alps of northern France. And I think I'll stop here, and if you have questions.
What about PhD? It looked like it sometimes not all of the observatories could see the target on the animation.
That's right. So I believe that view is from the direction of M87. So you don't have common visibilities of all telescope at the single time.
But they still use those baselines to create the end image, I guess. They don't.
Actually, I'm going to defer this to, I don't know if Jeff is here. I can certainly find out. Of course, I mean, one of the interesting aspect of this is time availability. So I don't know how they deal with that. Yeah, yeah. Yes.
Can you go back to the multiple baseline slide, please?
Okay. This one?
Yeah, this one. So still continuing my question from the last one, I don't quite understand, say for the first one, the x-axis is space.
This is the direction, yeah, yes.
But why does it look like a sine wave in space, but not time?
So this is the signal. You can think of signal coming from different directions.
Yeah.
Right. So that's your response. You have those waves. You have actually this pattern that coming, or you can think of. Let's put it this way. You actually this is a point source. Actually, yeah. you get spread. Your signal gets spread out in different directions.
Yeah.
In your primary beam of your antenna.
Okay, so maybe we can say it like if it's ball, then the wavefront is caused by the wavefront difference, because facing us directly, the center is going to be stronger than the others. It might have phase shift, causing it to be different.
No, in this case, actually, you can think of you're taking image. Your source actually is directly at your phase center. Yeah. So the wave is parallel waves, and the image of it is that you have the power of that source gets spread out in a different direction.
Okay. Okay, got it. All right, thank you.
All right.